Okay, thank you. So in this presentation, I want to discuss flooding mechanism of a rift and this period of transition with fluctuation between continental and marine conditions. And one of the only place on Earth, besides the Gulf of Corinth, where you find this is the Danakil Depression in Afar. And there are many people that contributed to this work and that participate in this big project, which is a collaboration between the University of Fribourg and the University of Addis Ababa in Ethiopia. Probably a lot of people among you are a bit familiar with the Afar region. So the Afar region is situated here. It's a triple junction between the Red Sea Rift, the Gulf of Aden Rift, and the East African Rift system. And the region experienced the eruption of the Ethiopian Large Igneous Province 30 million years ago, just before the start of the rifting. We'll now zoom on this Afar region and look a bit at the tectonic structure of the area. And it's a triple junction, but it's a bit more complex than simply three different rifts because you have this microplate in between the Arata microplate. And we can illustrate the movement that are happening there with a very simple model that shows that basically we have the Red Sea Rift that is propagating southward and the Afar Rift propagating northward. And this Arata microplate, this block is rotating counterclockwise. And this is important for the Danakil Depression, which is situated here in the northern Afar. So the Danakil Depression is situated partly below sea level, down to 125 meters below sea level. And I will now take you on a geological tour of the geology of the depression. And you can see on this lithostratigraphic map, all this blackish color, they represent volcanic material, recent volcanic material. The central part of the basin is very active with this regard. Then we have all this yellow and brownish color. They represent Sin Rift sediments, mainly clastic sediments. Then we have these blue colors, and these are the one we are interested in. These are the marine sediments, so they are mainly coral reefs and gypsum. And then we have this purple color that represent mainly evaporites, and in the central part of the basin, we have a lot of halite. And we studied the core here in the central part of the basin, and what we saw is that there are more than 600 meters of sediments that are dominated by evaporites. So all these purple colors are either halite or potash. And we studied this and we could see that the lower part, so below this arrow, they deposited in the marine water, and above this arrow, they deposited in the meteoric water, so continental water. So we think that the lower part is linked with the flooding of the depression, and we link them with the corals that we see on the margin of the depression. What do you find deeper? We don't know for the moment. There's no drilling, deeper drilling, and that's why we have an ICDP drilling proposal. That's the add-on project that Annelien Fuber presented to you during the last webinar of this series. Okay, so in this presentation, I want to discuss the when, the where, the how, the future, and then the lessons about the flooding of this Danakil Depression. And for the first question, the when, before asking for an age, we have to know how many times the sea invaded the depression. And we went to outcrops, we visited outcrop, and we saw several generations, several terraces. And on this outcrop, you see three here, but there's a fourth one that is higher up. There are a few corals that you would not see on a drone picture. So that means that this depression was flooded at least 4 times. And other people from the team, they have dated these terraces, and the youngest one dates to marine isotopic stage 5E, so approximately 130,000 years. So that's basically the last interglacial. Then the second one is MIS7, the interglacial before. And then the datings are a bit more uncertain for the next terraces, but they probably date back from MIS9 and 11. And that's logical. That's what you would expect. So the depression is flooded each time you have a sea level rise. For the question of where, it's probably not the most interesting, but the question from where is probably most interesting. From where did the water come from? And in the literature, most authors, they would say that it came from the Gulf of Sula. So that's here, that's from the north. It's along the rift axis. And there is a volcano there, the Alid volcano. And in the literature, they say that the eruption of this volcano would have dammed the depression and caused the isolation of the basin. And they describe marine sediment on this volcano. We actually think that this is not the true gateway. We think that the true gateway is from the Anfila Bay, which is here. And you can see this when I show the elevation map, and the elevation on the Anfila gateway is much lower. You're at 16 meters above sea level, while on the Zula gateway, you're at more than 200 meters. There are also fossil reefs that are described by some explorer there, and we could identify them on remote sensing. And there are also some problems with the explanation of the Gulf of Zula gateway, because first it's along the rift axis. So it's subsiding. So it should have been even higher in the past than now. It's not been shown that the Alit volcano is actually much younger than the last flooding of the depression, so that this cannot be the cause of the closing of this gateway. And probably the bivalve that they described as marine sediments, they were probably lacustrine, and this was not the gateway. But still, the Anfila gateway is at 16 meters, so that means that there was some uplift if the sea invaded the depression from this spot. And this we can check by looking at the paleo shoreline's elevation. And so we did a survey on the western margin. We measured the elevation of all these terraces, and because we know their age and the elevation of the sea level at that time, we could calculate the uplift and then the uplift rate, and we get the maximum uplift rate of approximately 1.5 millimeter per year. But the problem is that we could not go to the eastern margin. We tried again this winter, it did not work. But our goal is still to go there, and that's also why we did not publish this study, because we want to go there and really measure the thing. But by remote sensing, you can still see a few things. So this is a multi-spectral image of the gateway, and you can see two types of deposit. In orange, these carbonates, and in bluish, this gypsum. And we know that the gypsum was not preserved after MIS7. So this gypsum, we know that there are MIS5. And if you plot the elevation of these points, you see two clusters of elevation, one at 20 meters and one at 35 meters above sea level. And so our hypothesis is that the low one, which is the only one where we find the gypsum, dates back from MIS5E, and that the upper one where we find no gypsum is from MIS7. And so if we also assume that the uplift rates are more or less constant across the gateway, then we can reconstruct the elevation of this gateway through time and plot this with the relative sea level. And it works, it shows this uplift, and the tectonic movement is coherent with a flooding during the interglacials. We can then ask ourselves the question about the future of the depression, and we can first add the projection of the near future sea level rise. And it's not a good news, because anthropogenic sea level rise is likely to cause a flooding in the worst case scenario in 600 years. But for the further future, this gateway will probably not remain suitable for flooding the depression, because it's uplifting. So it will be more and more difficult to flood over. Conversely, the Gulf of Zula gateway will subside, and so will become more interesting to flood the basin. And we can make a very rough estimate of when this can happen by looking at these corals that you find there, that are on the rift shoulder of this graben. And from studies in the Gulf of Corinth, for example, you know that the subsidence to uplift ratio is approximately between 1.1 and 3.5. And so that would give you an age until this gateway reached present-day sea level, and that's assuming that sea level remains in the same ballpark as during the Quaternary, between 80 and 420,000 years. And that has interesting implication for the sedimentary record, because if you think we already had 4 floodings since 400,000 years, we now forecast several more floodings in the next 500,000 years. And remember, we have shown that the last desiccation cycle, and that's just the desiccation cycle, now that's not the flooding, that's not the open marine stage, just the desiccation cycle, produced more than 500 meters of sediment. So if each desiccation cycle produced more than 500 meters of sediments and a lot of evaporites in these, then we have the potential for the deposition of a very high thickness of synrift sediments in a very short time period. We can now ask the questions about the factors that are controlling this flooding of the basin. And we can do this with the graph that I've shown before to you. And it's obvious that the first order long-term controls are tectonic movement, the uplift of the margin, the subsidence of the central part of the basin, and that eustatic sea level changes, they form a second order, shorter term, high amplitude, high frequency control. But there are also other things. We have seen that anthropogenic sea level rise is a factor, so climate is a factor. Climate is also, of course, a factor for the type of sediment that you would deposit in the basin. And we, as part of the biosphere, we also play a role in this. Sedimentation and erosion also probably play a role. The Paleo Gateway might have been filled with sediment since the last flooding, or it might have been eroded, but we cannot say this from remote sensing. We need to go there to know this, but this probably also modulates the elevation of the gateway, because the blue line that you see here represents the present day gateway, but maybe it was not exactly at the same elevation.
That's just over 10 minutes.
Thank you. And there are other factors that might play a role also in the future. For example, we have said that probably in the future, the flooding will come from the north, and there we have volcanism, we have this Alid volcano, and so then the volcanism might play a big role at that moment, like it played a big role for the flooding of the northern part of the South Atlantic, where you have this Rio Grande rise and Valvis volcanic ridges that form a barrier and that play a major role for the flooding of this part of the Atlantic. But we can also think about mantle effect, because we have a hot spot. We have dynamic topography, and if you remove this dynamic topography to the topography of the region, you find a completely different topographic map. So the whole region would have been flooded since a very long time, and interestingly, also the coastlines of the Red Sea would be much more parallel than now. The tectonic context is also important, because remember here, we don't have a single rift that is propagating in one direction. We have a relay structure that forms this horst. And so it isolates the basin with a seal, with a gateway. And if we had just one single propagating rift, the flooding would probably have happened earlier, and eustatic sea level changes will modulate the flooding with more classical transgression and regression cycles without this catastrophic flooding and desiccation and all this evaporite. So if it was a single rift, probably would not have this evaporite, because it would be an open basin without a seal. And there are also other factors that play a role, but I will stop here and come to the conclusion and have some take-home messages. And for me, one important lesson from the Danakil depression is that there are multiple factors controlling the flooding of a rift basin, ranging from mental processes to climate, biosphere, erosion, and so on and so on. And these factors have influences over very, very different spatial and temporal scales, and they influence each other. So during one flooding cycle, one factor might be critical, but this might change during the subsequent flooding. And so each rift has its unique characteristic, and each flooding is probably unique. And I think that we cannot generalize this factor. And then a second point is that I think that this presentation highlights that a multidisciplinary approach is essential if you want to understand a rift as a whole. And if we want to understand the mechanism that controls its evolution, we have to be earth scientists and not just tectonician or sedimentologist or petrologist. And with that, I want to thank you for your attention.
Thanks very much, Valentin. That was excellent. So I open up to questions from the audience. Just feel free to type in the chat or put your hand up, or just speak out.
I have two questions from a non-expert. The first question, you mentioned corals. Are there other microfossils that you can track to fingerprint where the possible inlet was for the water?
Yeah, so there are tons of marine organisms. The problem is that, maybe I come back to this slide, is that there is a border between the western margin and the eastern margin. And the western margin is in Ethiopia, and that's where we worked. And the eastern margin and the Gulf of Zula is in Eritrea. And at the moment, we're working to get the permit to go there. And of course, if we go to the field, then it's much easier to do this kind of survey, because I mentioned that there were some marine sediments that were described on the Alid volcano, but that was a team that was studying the volcano. So they did very good observation. But they were not focused on these sediments. And so that's really our goal. We tried this winter, but we had to cancel because we didn't have the authorization. It's not easy to go in this region. But yes, of course, if we go there, then there's a ton of also paleontological studies that we can do. And there is also a coral paleontologist that work in our group and that did wonderful work on the taxonomy of the corals there.
Okay, perfect. And that answers my second question, which is why can't you get to the eastern side? So thank you for answering that too.
Perfect.
There's a question from Lisa.
Hi, Valentin. Thanks very much. That was really nice.
Hello.
I was going to cheat and ask Derek's question that he asked of me, which I don't think you did address, which is, do you think the sort of the oldest or upper limit of the corals that you find around the flanks of the basin are a function of preservation, or do you think they are marking the first time you had these incursions? I'm not sure if you addressed that. Apologies if you did.
Yeah, so that's interesting. I think the fourth terrace, we have seen it only on one outcrop, and it's a few corals, but they're higher than the third terrace. The third terrace is very clear. I can come back to this slide. The third terrace is very clear. It's this yellow one, and we have found corals that are, I think, 20 meters higher, and there are a few corals aligned. And so we think it must be an older generation, but we found only a few. And so I think that if there was a previous flooding, then we would not find it. It's the only outcrop where we found this fourth terrace. And we visited more than 30 different outcrops. So preservation is definitely something. But I think that if you go back that much in time, we would have to do the calculation. But looking at the subsidence of the basin, maybe the basin itself at that time was not anymore below sea level. And so even if the margin was below sea level, the basin itself was maybe higher. And so basically we don't know. I think the preservation does not allow to answer.
Yeah, that's what I wondered. Okay, thank you very much.
Any other questions from the audience? I do have a question about what is this Amphila gateway like geologically? Do you think it's a fault, like a cross-rift fault, or why?
That's a very interesting question. Maybe I'll go back to the geological map. That's maybe the best. So I'll use the pointer. So you see here in the southern part, these are all pre-rift rocks, and then they disappear. We don't see them. You have mainly sediments and some volcanic rocks, and then basement rock appear again here. Description of a small island of basement. You see also basement rock here, but I don't know exactly what it is. But it seems there is also, you see on some papers that were published about the seismicity, you see a swarm of earthquakes somewhere here. And if you look at the gravimetry, it's also one of the places where it's very low. So probably the crust is very thin here. I don't know. That would be a question for the geophysicist, and I would be super happy if this question could be answered.